Welcome to this lecture series in complex numbers. In this lecture, we'll be looking at this very nice problem. So it says that suppose alpha 1 up to alpha n are all the nth roots of unity. Then we want to show that this complicated expression is actually equal to a very simple expression. So as usual, you are encouraged to pause the video and or maybe think about it in your own time and then only come back to the solution that I'm going to present. The proof technique is what matters. It doesn't really matter what you get. How we get it is what I want to get across. All right, so the expression that we are looking to find the value of is this: k equals 1 to n alpha k divided by, what is it? 2 minus alpha k. This is the expression we want to evaluate, but what we will do is we will think of it like this: k equals 1 to n, 1 by 2 by alpha k minus 1. So all we did was we divided by alpha k in the numerator and denominator, which is legitimate because alpha k is non-zero, it's a root of unity. So this is what we want to compute, and what we are given is that alpha 1 up to alpha n are all the complex numbers satisfying this equation z to the n minus 1 equals 0. Because alpha 1 up to alpha n were given to be all the nth roots of unity, those are precisely the roots of this polynomial and hence precisely the solutions of this equation. And now, slowly, we will come to this. Right now what we have this, but slowly you will see that this kind of thing will appear. You'll see what I mean by that. So now 1 by alpha 1 dot 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 1 by alpha n are all the complex numbers satisfying this equation. Right, so just try to understand what is being said. If something satisfies this equation, its inverse will satisfy this equation, obviously. And conversely, if you have a solution to this equation and you invert it, you get a solution to that equation. And it's a very simple fact. It's not some theorem that I'm using. All I'm saying is substitute 1 upon alpha k here. What you will get is alpha k to the n minus 1. And therefore that is equal to 0 because alpha k to the n minus 1 is 0 just by virtue of the fact that alpha k is a solution to that equation. So just to make sure you understand this. Now this as such is not a polynomial equation, but you can make it in the polynomial form. Actually what you get is the same equation back. The reason is if alpha k is a root of unity, so is 1 upon alpha k. So these two statements are kind of the same statements, but now things start getting interesting. So now 2 upon alpha 1 dot 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 2 upon alpha n are all the complex numbers satisfying yeah, so what should I write here? This should be 1 by z by 2 to the power n. And to see that, call this beta 1. In your mind, call this beta 1, this beta 2, and then dot 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 beta n. So if we know that this equation has beta 1 up to beta n as their solutions, then which equation has 2 beta 1 dot 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 2 beta n as their solution? It will be this. Here you'll see a z by 2, because if you substitute in place of z 2 beta k, you will see beta k here, and then this becomes just 1 upon beta k to the power n minus 1 equals 0, and beta k was a solution to that guy, and therefore this is indeed 0. So we have got up to this point, and let us maybe massage this to a more better looking thing. So therefore 2 upon alpha 1 dot 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 2 upon alpha n are all the complex numbers satisfying 2 to the n minus zn equals 0. All I did was I just simplified this expression, and which is same as saying z to the n minus 1 z to the n minus 2 to the n equals 0. So I will not write the above one, I will write the below one. It's the same equation really. All right, now we want to come to this. So therefore 2 minus alpha 1 minus 1 comma dot 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 2 minus alpha n minus 1 are all the complex numbers satisfying. This time which equation? We'll do a z plus 1 here. Again, what is the reason? Let's say call this gamma 1 dot 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 gamma n. So gamma 1 up to gamma n satisfy this equation. And therefore, if you take gamma 1 minus 1 dot 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 gamma n minus 1, they will satisfy this equation, because once you substitute in place of z gamma k minus 1, you get this expression, which expression is nothing but gamma k to the n minus 2 to the n, but gamma k was one of the things that satisfied this. So just make sure you understand this also. Now finally we want to build that guy. So 1 upon 2 upon alpha 1 minus 1 comma dot 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 1 upon 2 upon alpha n minus 1. I just inverted all of them. Took the inverse of that, took the inverse of that. And same thing. Are all the complex numbers satisfying which equation? This is just 1 upon z plus 1 power n minus 2 to the n equals 0. And which is same as 1 plus z to the power n minus z to the n 2 to the n equals 0. Right? Satisfying this equation is as good as satisfying that equation. Just convince yourself. Is the computation correct? Yeah, it is correct. So this is a polynomial equation whose sum of roots is what we are trying to find. So that is the main observation now. These are all the complex numbers satisfying this polynomial equation. This thing is a polynomial. And how do you find sum of all the roots of a polynomial equation? Of a polynomial, you collect a certain coefficient and whatnot. So that is what we are going to do. So this looks like z to the n 1 minus 2 to the n. And all we are interested in now is in the coefficient of z to the n minus 1. And the coefficient of z to the n minus 1 is n because of binomial expansion thing. So it is something like that. All we are interested in is the coefficient of that and the coefficient of that. So we have figured both of them out. And therefore, the sum here, the sum of all the roots, which is that thing, is minus the coefficient of this divided by the coefficient of that. So that sum is minus n divided by 1 minus 2 to the n, which is n by 2 to the n minus 1. Right? So just think of, generally this kind of thing, when I see this kind of expression, I try to think of them as roots of some polynomial and use the Vieta's theorem or whatever you want to call it. Right, so just all you should know for this problem is that sum of roots of a polynomial can be computed by looking at coefficients of certain terms, and there are other things that you could compute by the same idea. For instance, perhaps you would like to know the product of all of these. That also is something you can compute. Anyway, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.